Okay, thank you for the introduction. So I'm Bruno Quesson. I'm working here. So I'm going to give you an overview about what we are doing here in the field of interventional cardiac MRI. So to give you some ideas, what we are doing is the first application that we developed was trying to measure the temperature change inside the cardiac muscle when you are doing a radiofrequency ablation. So for this, you need to be able to map the temperature change and dynamically. So for this, we use gradient echo-based sequence, rapid gradient echo-based sequence, because the frequency of the MR signal varies linearly with temperature over the range of the between up to 100 degrees. So basically, you can map this temperature change into the phase as a function of time. And of course, for this, you need to do dynamic imaging, process the imaging in real time to extract the temperature change that you will plot on top of your magnitude image where you are, where you want to treat. And of course, this must be done in real time. And if you're able to do that, the idea would be that you can make a feedback control and control energy delivery with a given device, whatever the device it is, and then have a fully automated procedure in order to make the procedure fast, robust, and accurate. So why and how measuring temperature? I'm not going to give you a deep overview of how we measure temperature because we have a talk tomorrow by Valérie Ozen. And basically, you can see here on the top magnitude and phase images acquired on a piece of meat before any induction of heat and after a local induction of heat. So you can clearly see they have a contrast in the phase images. If you subtract that and multiply by a constant depending on the TE, your echo time, and etc., you can color code this temperature change and plot this on your magnitude image. So why do you want to do that? It's because if you're able to map the temperature change in space and time, then you're able to compute what we call a thermal dose. This is a temperature curve that you can measure in a single pixel as a function of time. And basically, it's a bit more complicated than that, but the idea is that the area under the curve gives you the accumulated thermal dose, and this can be used as a therapeutic endpoint. So the idea would be to use real-time MRI to compute temperature changes, then compute in each pixel the accumulated thermal dose and try to show if this can be a clinical endpoint. You have here an example of the temperature change that you see during the experiment. So that's okay, actually what we are doing movie images. So what we use for why did we start up with this project is because during radiofrequency ablation, the key point is that are you able to make a full transmural lesion to treat to make a small burn over the full depth of the myocardial wall. And the issue is that due to motion, you can have a poor contact between your catheter and your the myocardium, and as a result, the energy that you apply with, for example, radiofrequency ablation has a poor impact on increasing the temperature in tissue, and you may result into incomplete treatment. So the first idea was to increase the power, but if you do that, you may induce some burn at the contact, and then you have no more electrical conductivity. So the RF energy that you apply does not contribute to heat the tissue anymore. And in extreme case, if you increase too much the power, you can create boiling, and this create a crack into the cardiac wall, and this is an issue, of course. So in order to try to measure temperature change using MRI, so this is a highly challenging task because then you need to have temperature uncertainty in a range of 1 or 2 degrees. You need to have a fast update rate, so you need to use fast acquisition. How did we do that? We implemented EPA-based sequence with triggering on the ECG with the electrodes positioned on the thorax and making, for example, a navigator to compensate for respiratory motion. The problem is that you usually make a lesion of very small dimensions, so you need to have a quite good spatial resolution in the range of 1 millimeter or better. And of course, you need to deal with these two motion. And using this strategy, we're able to acquire 5 slices every heartbeat, and using a combination of a navigator of fast saturation and a single shot EPI with parallel imaging. So for this, we use the standard 1.5 Tesla magnet with standard equipment. This is the sequence, and we implemented, thanks to mainly under supervision of Valérie Ozen, a full pipeline for real-time image reconstruction using the Gadgetron environment. And after that, we also implemented the MR thermometry pipeline that I'm sure is going to present some details tomorrow. And then after that, you need to have a display console to visualize the images in real time. So this is an example. What you can see, the first point was what's the uncertainty of the temperature estimate as a function of time. So you have an example here of a healthy subject. You have 5 slices, so you can note that the blood is cancelled very well cancelled in this slice, but poorly cancelled there. But what we do, we repeat the acquisition, so we get magnitude and phase images over a different number of several slices, several cardiac beats, and then we compute in each pixel after compensating for motion and susceptibility-related artifacts on the phase images. You compute the temperature change, the apparent temperature change without inducing any heat, and then you can, in each pixel, compute the temporal standard deviation of the temperature. So what you can see here, with a spatial resolution on 0.8 by 0.8 by 3 millimeter and 5 slices per heartbeat, you can see that your temperature map, which is color-coded dead, is reasonably good, except in this area, which is at the intersection between the heart, the lung, and the liver. This is an example of an animal experiment. This is an ablation in a sheep where the catheter is there, and you can clearly see that over these 5 slices, you can see the temperature change with a full field of view. This is a zoom view of the temperature change, and this is the accumulated thermal dose and here what we color in red the pixels that have reached accumulated thermal dose of a given value, reference value. And then the idea was, is this metric a good indicator of the actual lesion size? So for this, we used a published method by Dr. Gutmann. And the idea is to use the same sequence as the LG, but without injecting the contrast agent, but changing the inversion time. And doing this with a long inversion time, you can clearly have an impaired signal where you have burnt the tissue. You have a normal signal around in the healthy tissue, and in between you can see the edema as a hypointense signal. And what we did with the 3D acquisition immediately after the treatment, we compared the size of we measured on the 3D images with the size we measured on the thermal dose images, and with the dimension of the ablated region after we expanded the heart. So these are the correlation curves, and what you see is that we have very good correlation. So in other words, we can use MR thermometry and dosimetry to predict the lesion size. So these were on animals, and then Valérie did another study on patients at the hospital, because here you also have to deal with patients who are arrhythmogenic. So this is an example of the ECG that you get, images that you get with temperature maps. Of course, here is without any ablation. And what we did is that we analyzed the stability of the cardiac rhythm by plotting the error interval at a given time as a function of the previous one. And if you have a patient whose heart is beating completely regularly, you will get a single plot, a very localized plot there. Then if you start to have, in this second patient, a bit of arrhythmia, you can clearly see that you have a split of this value in different areas. And in extreme case where you have a very highly arrhythmogenic patient, you can do some clustering to analyze the data. But even in that case, in this worst case, you are still able to map the temperature with a reasonably good precision. However, we still, as I said before, we are still in a situation where the spatial resolution is sufficient. So we also investigated the idea of making small coils, so small MR receiver coils. So an example of prototype designed by Marilyn Delce during her PhD thesis. So it's a 2 centimeter coil with the tuning capacitor and the matching capacitor and the tuning hardware. So this is quite classical technology. And then with this, the advantage is that if you put this on a phantom and you measure the gain in SNR that you can achieve with such a coil, you can reach up to a factor of 35. So in other terms, you can convert this gain in SNR in a reduction of the spatial resolution. And the other point is that since you're only able to image a small area around the coil, you can also reduce the field of view and then accelerate the acquisition because you have less data to acquire. So this is the idea. So this is an example. These are examples. First, we tested on the left atrium of a ship that was collected and put into a tube. So you can, for example, see images in 3D with 300 microns isotropic resolution. So it's an example. On the septum of a ship, here you can see the 3D images. You go slice by slice, and you can appreciate the image quality at 200 micron isotropic resolution and 1.5 Tesla on the clinical scanner. So that's nice, but that's ex vivo tissue, and we want to scan tissue in vivo. So what ideally in vivo? So the intermediate step was to exploit a device that we developed a few years ago. So this is on this trolley. You can put some equipment and do surgery on a pig or a sheep, collect the heart as you would do for cardiac transplantation, then resuscitate the heart and make the heart beat inside the MR scanner. So this is, you have a photograph here with the heart here, and you can attach the coil to your coil with to a holder and position next to the heart and do acquisition. And of course, you have to deal with cardiac motion, and we instrumented the ex vivo beating heart using a pressure sensor here, and we can collect the pressure from the left ventricle and then use some basic hardware to trigger in the sequence to collect the data always at the same cardiac state. So these are examples on the beating hearts from pig. What you see are 3 examples here, and you can appreciate the images with something which is close in terms of spatial resolution about what you can get in vivo. And if you increase the spatial resolution here, you can clearly delineate much more clearly the internal wall structure of the left ventricle. In this example, you can also appreciate by that you start to see some fiber orientation. In this example on the right, it was more to see some anatomical details that you can appreciate, and particularly if you look at this small arrow here, you can start seeing a very, very small vessel that is here. Okay. And last, you can appreciate with this high spatial resolution, this 170 microns in plane resolution by 1.5 millimeter slice thickness. You can clearly see on the left ventricle, the myocardial wall, you can see some structure that are hardly accessible with conventional MRI. Of course, here you are outside you're in contact with the heart, and the idea would be at the end to make a catheter that you can deploy inside the cavity. The advantage of such a technology is that you can also increase a lot the precision of the thermometry. This graph shows on the gel sample, this is an acquisition where you heat there, and then you compare 2 acquisitions with a standard chest coil, and then adding a small coil there. You can clearly see that you have a much higher signal-to-noise ratio, and of course, the higher is the signal-to-noise ratio, the higher is the precision of the phase estimate, and as a consequence, the temperature estimate. So you can clearly see here that the orange curve shows the standard uncertainty of the measurement of temperature during a heating. And if you simply use the coil itself alone, you can go from the orange curve to the green curve, which is much more precise. And you can then turn the situation the other way around, not keeping the same field of view, but then reducing improving the spatial resolution of your images. And then if you do a very tiny heating using, for example, here a laser, you can clearly see that increasing the spatial resolution, of course, decreases the partial volume effect of your temperature estimate. And instead of estimating a maximal temperature increase in this example of 5 degrees, simply by increasing the spatial resolution, you can measure that the actual temperature increase is much higher. So this means that using this technology, you should be able to see at the same time better details on your cardiac anatomy and also better monitor the treatment. So this is a very, very first prototype of a MRI compatible catheter. This is a collaboration with colleagues in Lyon. So this is basically a Foley tube that you with an inflatable balloon at extremity, and when you inflate the balloon, you shape the receiver coil. All these coils, all these components are going to be removed and miniaturized, and also we are working a lot on how to do active decoupling remotely. And this is an example of the signal-to-noise ratio you can achieve with such a very small coil. So we hope that in this year we're going to install in our facility all the equipment necessary to develop our own catheters, and this is one of the projects we'd like to develop. I wanted to continue this cardiac interventional MRI by combining MRI with another technique, which is focused ultrasound. So what is focused ultrasound? Well, we have heard about ultrasound imaging. So basically you see a probe here, and you can focus the ultrasound waves to a given location, which is called the focal spot. And for imaging, you have a low energy, but then if you have the possibility with a dedicated emitter to increase the power, you can use very short pulses to, for example, use mechanical effects of the interaction between the ultrasound wave and the tissue. Or if you use lower power but much longer duration, you can also induce temperature change and do thermoablation. And the advantage of that, this technique, is that it's totally non-invasive because the transducer can be positioned on the surface of the skin. Okay, so let's talk about a first application about non-invasive cardiac stimulation. So this is again an example of beating heart inside the magnet. So this is the heart from a pig, left ventricle, right ventricle. You have underneath the ultrasound emitter, and you can select from the MRI images where you want to sonicate. You want to apply pulse here. And then what we do is that you have here the electrical signal from the right atrium, the left ventricle, and you see that the right atrium depolarize before the left ventricle, which is normal. And if you send ultrasound pulse here, an ultrasound pulse in this refractory period before the T wave, that nothing happens. But then if you send the same pulses after this T wave, you can induce a premature ventricular contraction, so you can modify the cardiac rhythm. So the idea here, we have a European grant for that, to develop this, to develop diagnosis against the risk of sudden cardiac death. So this is an example of what you can do. So it's just because we are close to noon to wish you guten Appetit. So this example of a beating heart of a pig, and then we are going to send ultrasound pulses, and what you see here is that you can force the heart to beat at the frequency of the pulses you are emitting. With the same idea, I said before, we show that we have the feasibility for stimulating the heart, but we could also try to do ablation. The issue is that with conventional large-scale emitter that is designed to send high-power ultrasound pulses, you intercept the bones from the costal grid, and using this, the issue is that these ribs absorb a lot the ultrasound wave, and then they retrodiffuse the heat to the surrounding tissue. So the issue is that you're going to burn the intercostal space here in gray, and all the energy that is sent into the bones, of course, doesn't go to the targeted area inside the heart. So for this, we design an intercostal, the dedicated intercostal a transducer that with the dimension here and the generator here. We're also working on developing a new one that is much more powerful. And using this, the question was, okay, can we characterize what you can do? As I said before, you can do MR thermometry, forget this at this time. And here you have a sequence, which is basically an EPA sequence in which you add a pair of gradients, like for diffusion. And then if you synchronize the ultrasound pulse, which is called SRF, at the same time with the gradient, you're going to encode into your phase image where you have your push. Okay. And the issue is that if you send power at the same time for heating, which is not shown here, then you can have in the phase image the contribution of both the push and the temperature change. If you do repetitive imaging, you can, from one acquisition to the next, change the polarity of your motion encoding gradient here, this bipolar gradient. And then this means that for a given dynamic acquisition, you get a subtractive combination of temperature and displacement. And the next one, you get an additive. And simply by making sum and differences between successive images, you can retrieve both the temperature and displacement map. Here you can see an example. The transducer I showed before is positioned on the left, shoots there into a gelatin gel. This is an experiment done by Fanny Labrun and Mathieu Guyot. And what you see here is that with your transducer, you can send your power here and change the localization of your push, and you can monitor this in real time, where you are pushing your tissue and where you're going to send your energy. These big red things that you see here is because you have a change in the impedance. This is a gel. You have the impedance there, and you have a reflection of the push there, and this is simply an artifact. And so this was a sequence published and a method published a few years ago, and we are now working with Nadej Korban to implement a much faster acquisition method. So what you can do with that to characterize your device, for example, here you have an example of oh, I should finish. Okay, this is not my last slide, my last is the next one. So you have an experiment here where you put a sample, we put ribs next to that, and you have your transducer sonicating here. What will you do? You change the intercostal distance between the two ribs to see up to where you can go and can we sonicate in between the ribs. So this is an example here where you have displacement and temperature, and you can see this graph where you increase the power without the ribs, so you have the displacement and no heating in between the ribs. And then if you have the ribs spaced by 1.8 centimeters or 1 centimeter, you have no significant change. But then if you reduce the space to 0.8 millimeter, then you start to see a decrease in displacement. And this means that you have much less energy going there. The second experiment was introducing a rib cage here and see how much this attenuates. So using MRI here is to characterize the capability of the ultrasound device to sonicate, with the idea of both being able to stimulate in a safe way and also potentially to induce non-invasive cardiac ablation without using any catheter. So this is my conclusion. Interventional MRI for cardiac application is really challenging. You need fast acquisition, online image reconstruction, and fast image processing and display. You can make the contrast in images sensitive to temperature and displacement change. And you can use a force MR for planning, monitoring, and post-ablation assessment. And you can combine MRI with a different MR-compatible ablation device. Thank you.